Okay, so this is the last of the 4 lectures, although in your case there are actually 5, because as I said on Wednesday I made a mistake and I taped the Diene lecture as well. So you don't have to look at the Diene lecture, just the last 4. And I just sort of noticed that we were going a bit over time on those. I had meant for those just to be, 25 minutes to half an hour, and we're a little bit over, so I've got my alarm clock set. So we're looking at Diene chemistry, and this is Diene chemistry 3. And so we ended last time by identifying, by being able to identify which dienes were more active than which, and essentially the more electron releasing groups you have, and particularly those that are electron releasing by resonance, then the more active is a diene. And conversely, in a dienophile, the more electron withdrawing groups you have, particularly those that are electron withdrawing by resonance, then the more Diels-Alder active they are. But you may have been a little bit concerned, because when we looked at the diene, and again the dienes are always in the S-cis conformation, it's easy to see that a diene can react with an alkene as a dienophile, and we end up getting as our product the corresponding cyclohexene. That's fairly easy and kind of straightforward to follow. And even if there were groups attached to my diene, let's say for example I had a methoxy group here and a methoxy group here, and even if I had a cyano group here and a cyano group here, so this would be a very fast Diels-Alder reaction, a very facile Diels-Alder reaction, because I've activated both the diene and the dienophile. And what that translates to is that, for example, let's say if I mix butadiene and ethene, I'd have to heat that at 200 degrees Celsius for 6 hours to get any really good yield of cyclohexene. Right? But for this reaction I just wrote, that's probably going to be maybe 80 degrees Celsius for an hour before I get appreciable yield. And what will I get? Well, I'm going to have a methoxy group here, a methoxy group here, right? Because again, this carbon and that carbon are these 2 carbons. And in my cyano, I'm going to end up with them, since there was cis in the solid material, I'll end up with the cyano groups here and the cyano groups here. Okay? Well, the next issue to address is what happens if the diene, the dienophile, and the diene look a little bit different. In other words, let's do one at a time. What would happen if I reacted these compounds? Let's say I have NO2 here and NO2 here. So this is an activated dienophile, because I have 2 electron withdrawing groups, 2 very potent electron withdrawing groups attached to the dienophile. This is also an activated diene, because I've got 2 electron releasing groups, only by induction, attached to the unit. So I'd expect this to go maybe not as quickly as this one did, right? But certainly faster than the reference reaction, right? Which will be prohibitively slow, because neither the diene nor the dienophile is activated. So what would I get? Well, it's a Diels-Alder reaction, and Diels-Alder reactions give rise to cyclohexenes. That's the first thing you do, because once you recognize it's Diels-Alder, you just draw the cyclohexene. You draw the double bond in that part of the ring that really is the descendant of the diene. So again, these 2 carbons will be these 2 carbons. Okay? Now, attached to these 2 carbons in the precursor molecule were methyls. They were not involved in the reaction, so they're still there. There's a methyl here, and there's a methyl here. Well, these 2 carbons are here. Okay? And if you look at the way we draw the reaction mechanism, one of the pi bonds in my dienophile is involved in the chemistry. The other one is not. So that pi bond is not involved in chemistry, so it remains. Okay? So I used this pi bond, if you will, to form this sigma bond. That's here. Just erase that part so we do this a bit more easily. I'm using this pi bond to form this sigma bond. I use this pi bond, right, to form this sigma bond. I use this pi bond to form that pi bond. So all I've basically done is I've reallocated electron density. Some pi's went to pi, some pi went to sigma. On these two carbons, I had nitro groups. Well, they're not involved in the chemistry, not directly anyway. I mean, their role in this reaction is to facilitate it, right, by activating the diene. But in terms of, you know, anything else, they're not really involved in the chemistry. So the product of this Diels order reaction would be this dinitro species that I've drawn. And I expect this reaction to be pretty facile, maybe maybe 100 degrees, maybe 100 degrees Celsius for 3 hours or something before I get a good yield of product. As compared to the conditions I used for the one above, which was about 80 degrees for an hour, because this is a super activated diene and a pretty activated dienophile. So again, what would happen if my diene this time looked a little strange? What if I started off then with a diene that looked like this? In other words, if I started off with 1,3-cyclohexadiene. If I react that, for example, with this compound, okay, that would be a fairly facile Diels order reaction again, because both the diene and the dienophile are activated. The diene is activated by the alkyl groups, and there are two of them, much like in this scenario. The dienophile is activated by electron withdrawing groups, the two cyanos, much like in this scenario, although nitro is a much more potent electron withdrawing group than cyano. And of course the reason is the nitro, in addition to having X double bond Y, has a positive charge on it. And if you remember all the way back when we were describing the effects of the characters of electron withdrawing groups, we said we could be electron withdrawing by resonance if I have an X multiple bond Y, and also by induction. So the nitro group is a combination of both, right? The nitro group utilizes both induction, because I've got X plus, and I also utilize resonance because I've got X multiple bond Y, where these two are, it's a heteronuclear bond. So nitro, in fact, is the world's most potent electron withdrawing group. So what about this reaction? Well, I recognize this as being Diels order. And so, you know, I'm not going to be dismayed. I'm just going to draw a cyclohexene, because the product of a Diels order reaction is the corresponding cyclohexene. I'm going to draw my double bond there again, and we're good to go. So I need to identify where my pieces are. Where are things coming from? And again, without making life too hard, this carbon and that carbon, my two markers. This carbon and that carbon are my two markers. Where are they? Well, the two dark ones are here and here. And the X'd ones are here and here. Well, attached to these two dark carbons was a 2-carbon bridge, a bimethylene bridge. They did not participate in the chemistry, so they're still there. There's a bimethylene bridge. Right? They did not participate in the chemistry, so they're still there. Okay, let me erase this to clear this up a little bit. Alright, so they are still there. Similarly, attached to these two carbons, there was one pi bond, and this pi bond was involved in the reaction, but the other one was not, so it is still there. And attached to it are my two cyano groups. But what I've generated here then is really a bicyclic molecule. So one of the things you notice is that if my Diels order reagents are acyclic, then I will generate a monocycle, right, which is the 6-membered ring. If one of my reagents is cyclic, then I'll generate a bicyclic product. As we'll see later on, it gets a bit more complicated. Well, this species can be drawn the way I have it, but it can also be represented in the more familiar fashion, which is this. Right? That is the product of your reaction. these two species are the same. Right, so just to walk away around the system, if I were to number these, and I'm using a bad numbering system here, but if I said 1, 2, 3, 4, 5, 6, 7, 8, well, these are 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's the product of this Diels-Alder reaction. You also want to be aware of the fact that sometimes the systems will be written in an awkward fashion. Like I could give you what do I get when I react this molecule with this compound. Say, let's realize it's Cl and then NO2, right? And I heat that at 120 degrees Celsius for 3 hours. What do I get? A lot of times students say, well, geez, look, it's high temperature, therefore I'm going to be getting an E reaction. Well, that's not true at all. The problem here, of course, is that both reagents are written in an unfamiliar, in a fashion that is not Diels-Alder friendly. And you have to recognize, look, I've got a diene, which must adopt and can adopt the S-cis conformation. I have a dienophile, right, with my nitro and my chloro on it. So I'm just going to get a cyclohexene as my product. Right? I'm going to get a cyclohexene. So I'm going to draw my cyclohexene product, yada yada, and I'm going to have a double bond here as well. I'm going to have a Cl and then a nitro. Okay? Well, it gets a little more interesting if we draw a species that looks, for example, like this. Oh, but since I've drawn this already, let's take a different example. Let's take this one. So let's take cyclopentadiene, and let's react cyclopentadiene with succinic anhydride. Okay? Well, what will we get? And we have to recognize that this is a diene and that this is a dienophile. And if I recognize this as being a Diels-Alder reaction, then I know my product is going to be a cyclohexene. So let's go ahead and draw the cyclohexene. Man, that's a whopping big cyclohexene. Let's just clean it up a bit, shall we? Hey, Ma, look, no chalk on my hands. So I'm going to get a cyclohexene. Again, this carbon and that carbon are here and here respectively. So this methylene bridge, which connected the two vinylic carbons, the proximal vinylic carbons if you will, that methylene bridge wasn't involved in the chemistry, and so it's going to remain here. This pi bond in the succinic anhydride was involved in the reaction, right? It was used to form, in fact, this sigma bond. But this group, these two carbons, are still here, and attached to them are still this anhydride unit. But this is really a cis double bond. And I know that the Diels-Alder reaction is highly stereospecific, which means the cis alkene must give rise to the cis product. Right? The cis alkene must give rise to the cis product. So the product of this reaction, I'm going to draw like this. So I'll have C double bond O. I didn't even need to draw the C. It's a little easier. Right? And then O, that. Okay, so if I clean it up a little bit, then my species would look like this. And if I just stick to the bond life formula, that's what my species will look like. Now, there is an issue here, which is that, again, these bonds are going to be cis to each other. And you might immediately realize, well, look, there's a problem because let's say these bonds are pointing forward towards you, or towards me. So these are up, right? So this entire substituent is above the plane of the page. This methylene group is also above the plane of the page. So this entire unit, if it's pointing up, is actually cis to this methylene. Now, if they were both pointing down, if these were both pointing down, so it's behind the board, this methylene is still, as I've drawn it, pointing up. Which means I can be cis with the substituent pointing towards this bridge, and cis with the substituent pointing away from the bridge. In other words, I'm actually making two different cis compounds. How would I represent those two compounds? And the answer is I represent them like this. One cis product will look like this. So this is my 6-membered ring with my double bond, and it's pinched across carbons 1 and 4 by that methylene bridge. The carbonyls could both be down, okay, and then bridged by your anhydride function. This is a scenario where these groups are pointing down and this is pointing up. There is another scenario in which my methylene bridge is pointing up, and now both of my carbonyls are also pointing up. And they are bridged by that anhydride function. Now, both of these compounds, by definition, are cis. They are cis substituents, because my carbonyls are on the same side. But clearly, I couldn't just call these compounds cis, right? Because whatever I name these compounds, and these are tricyclics, whatever I name these compounds, just like I call a compound Frank, I can't call this cis Frank and call this one cis Frank because they're two different compounds. And we've seen this problem before. We've seen this problem before when, for example, we had this butene and we had that butene. They're both butenes, but I can't call two different compounds by the same name. So I make up a label that calls this one cis-2-butene and I call this one trans-2-butene, right? So often in organic chemistry, we have to come up with labels to distinguish one species from the other. We saw exactly the same thing with the RNS. So what kind of label can I use now to distinguish between these two cis compounds? Right? What kind of label do I use to distinguish between these two cis compounds? Compound 1 and compound 2. These are isomers. They're both cis isomers. And the label I'm going to use is endo and exo. Right? I'm going to use the labels endo and exo. So which is which? Well, if you look, this species has my substituent, which is relatively bulky, pointing towards the bulkier bridge in the molecule, right? So I'm going to have an interaction in the sense that my substituent is pointing towards the larger, in this case a 2-carbon bridge in my product, right? So again, if you remember your way around a bicyclic, here's my bicyclic, and I've got a 1-carbon bridge, a 2-carbon bridge, and another 2-carbon bridge. Now, I don't consider this 2-carbon bridge because that's where my substituent is. And my substituent, all of it, is pointed towards the bigger of my bridges. So I'm going to call this the endo isomer. In my compound 2, my substituent is pointed away from the bigger bridge. So the big bridge is pointing down, and the substituent is pointing up. So I'm going to say my big bridge, my substituent, is pointing away from my big bridge. So this is the exo compound. So I have the exo compound and the endo compound that are formed when cyclopentadiene reacts with succinic anhydride. Right? I make the cis species. It just turns out that I have two different cis species. I have the endo compound and I have the exo compound. Right, so we just talked about the fact that we can make either the endo, in fact we make both the endo and the exo compounds. So the question organic chemists will always ask is, fine, if I'm going to make two products, can I control my reaction to make a preponderance of one over the other? Can I doctor my reaction conditions to make principally the endo compound, or exclusively? Can I doctor my reaction conditions to make principally or exclusively the exo compound? And the answer is, we are organic chemists, we can do anything. So the answer is yes. But in order to understand how to control the conditions, we have to understand what the system is doing. In other words, what are the steric and electronic issues and orbital issues involved in formation of both the endo and the exo compound. You will remember that we talked at length in 301, in First Organic, that the fates of organic reactions and the properties of organic systems depend ultimately upon the interplay of three factors. They were electronic factors, they were steric factors, and then there were issues that involved orbital overlap. Okay? Although many people argue electronics and orbital overlap are very similar. So what I've done here is I've constructed a model of both the exo and the endo compounds, the exo and the endo isomers. This one, as you might be able to tell, is the exo species. Okay, and I'm hoping you guys can see this well in the camera. And so this would be my methylene group, right? So I'm going to hold my methylene group, that's here. Okay, this is my methylene group. This represents the carbon-carbon double bond, which is here. All of this would be the six-membered ring, that is this bit. And then I've got my C double bond O, the O's are blue. So C double bond O, C double bond O. The carbon is attached to an sp3 hybridized oxygen, that's here. That's attached to another carbonyl group, that's here. And then the carbonyl carbon is bound to the ring. So this is my exo compound. So I'm going to turn it around so you guys can see, and I'm hoping this comes out well. Right? That's my exo compound. Its isomer is the endo compound. Okay, and this time you can see that I'm going to hold it the way I have it on the screen. Right, so here is my carbon-carbon double bond, right, in my six-membered ring, pinched across carbons 1 and 4 by the methylene. So carbon-carbon double bond in my six-membered ring, right? Carbon-carbon double bond, six-membered ring, pinched across carbons 1 and 4 by the methylene group. And I've got my C double bond O, C double bond O unit, my anhydride unit, that is pointing down. That's down here. So this is the endo compound. Again, I'm really hoping you guys can see this, and if not, I'll do it again in class when I come back. Okay? Or you can build the models. I mean, building the models is a good idea. So the question I'm going to ask is, well, fine, what are the factors that affect the formation of the endo compound? Let's pick the endo. If I hold the endo compound, and I'm going to stand a little further from the screen, okay? If I hold the endo compound, you didn't know I was sitting, did you? You can probably see that I've got my carbonyl group here, right? I've got my carbonyl group here and carbonyl. Behind the carbonyls, or exactly behind them, is my carbon-carbon double bond. So what happens is, as I'm forming this endo compound, the p orbital on the carbonyl group, overlap with the p orbitals of the pi bond, the carbon-carbon pi bond, exactly below them. That overlap is bonding. Bonding stabilizes. So the transition state leading to the endo compound is actually stabilized because of pp overlap. And so formation of the endo compound is easy. There is no such stabilization in the formation of the exo compound, because the p orbitals on the carbonyls, they are running in this direction. The p orbitals on the carbon-carbon double bond are running in this direction. They have no contact whatsoever. Without that overlap, there is no stabilization in the formation of the exo, and so the formation of the exo compound is more difficult. Okay? So formation of the exo is not assisted by any overlap, and therefore it is relatively difficult. No pp overlap. Formation of the endo is assisted in the transition state by pp overlap, carbonyl, so carbon-carbon double bond, carbonyl to vanillic carbon. And that pp overlap in the transition state stabilizes the transition state, and that makes the reaction facile. Okay, so what's the consequence? What's the consequence of that? The consequence of that is, I'm just checking my time to make sure I don't go over. The consequence of that is the following. If you look at a reaction profile diagram for formation of the exo and the endo, I can represent it as follows. Let's say that this is the energy level for my diene and my dienophile. Okay? That's the energy level for my diene and my dienophile. We are saying that the pathway to the endo is relatively facile, but the pathway to the exo, oh my god, that's an awful looking thing. The pathway to the exo is more difficult. Okay, it's the pathway to the exo compound. Now, if we look at the exo and the endo compounds again, and I don't think I need my models to illustrate this, my substituent in the endo case has this big group, right? My product has this big substituent pointing towards the big bridge. So there's going to be a massive interaction between these that is steric, and that will destabilize the endo compound. There is no such destabilization in the exo compound, right? My large substituent is miles away from my big bridge. In fact, if anything, it's pointing towards a smaller bridge. And so the endo compound is actually the one that is more unstable because it has a higher energy content. So the endo compound is the one that is more stable. Which means, the endo compound is the one that's more unstable because it's a higher energy content. Which means when I form my endo compound, I grant you I will form it quickly, but it's a relatively high energy species. The exo compound is formed more slowly, but it is a relatively stable species. Does this look familiar? Right? It's exactly the scenario we had when we looked at the reaction of dienes with HCl, the polar addition. So what this means is that if I wanted to form the endo compound, I would run the reaction at low temperature for short exposure. Right? Low temperature for short exposure. Right? Short time. If I wanted to make the exo compound, I'd run the reaction at a high temperature, right, for prolonged exposure, right, or long exposure. Okay? And the reasons are exactly the same as we described before in the polar addition. And so you may want to go back and look at that discussion. So basically, the formation of these endo and exo compounds are also subject to kinetic versus thermodynamic control. Right? And it's another issue, another example of where the more stable compound, in this case the exo compound, does not form more rapidly. That is, the less stable compound that is kinetically favored. So the endo compound in this case is called the kinetic product, the thermodynamic product being the exo compound. Alright, the very last thing we're going to consider is if we can figure a way out around Diels-Alder reactions. Okay? And we probably will not finish this discussion entirely, but we will simply get as far as we can and then move on from this. So just maybe another 5 minutes. So, for example, let's say I asked you, suppose I want to make a particular compound. And let's say my intent is to make, let's say I want to make this compound. Let's see. Okay, let's say I want to make this compound, and I want to make it using Diels-Alder technology. What do I need to make it? Well, I'm going to say, if I look at this molecule, I have a cyclohexene, and therefore it would certainly be synthesizable via Diels-Alder. So one option is, I could simply say, well, these 4 carbons could have belonged to my diene. In other words, I could have started off with this set. Therefore, since I'm not seeing a double bond here, my dienophile would have a vinylic group attached to which I have O, C, O, C. In other words, if I were to clean that up a little bit, what I actually would have as my starting material would be this compound. And if I mix those two, I would certainly be able to get this reaction and get that product. So that's one way of looking at it. There is an alternative, and the alternative is, well, what if I said that I'm going to use these 4 carbons, 1, 2, 3, 4, as my diene, and this part as my dienophile. In which case, I would be able to make the compound starting from here. My diene would look like this, to which would be attached O, methylene O, and my dienophile would actually have a carbon-carbon triple bond. Okay? Now, I won't directly make that compound. What I'll make would be, there's a lot of room here, won't I? Yeah. What I'll make would be this species, double bond here, and a double bond here, and then I'll have to selectively, which will actually be very easy, selectively reduce this compound into that one. So I would just say selective reduction. In other words, I'm going to reduce this double bond rather than that one. And I'm just going to point out, this double bond is very active because it is being given electron density by not just 1 but 2 oxygens, right? What I have is an activated vinylic group, right, which is going to be able to accept electron density from not just 1, but from 2 oxygens. So that's a very active one. So in fact, the way I would do this, and you're not responsible for this, but I would use the weakest hydrogenating agent I can think of. That would be able to convert this one, but not that one. Okay, and that's the sort of logic we would use. But anyway, I would do a selective hydrogenation to make my product. So the question is, which of these two is the better method? And I can say, well, the problem with the method on the left is that it has 2 steps, 1, 2, and that's more work. Whereas the one on the right has less work because it's 1 step. But if you look at it carefully, the method on the right has a drawback, which is my diene is not activated. My dienophile has electron releasing groups on it, 2 of them. And not just any not just any old electron releasing groups, but they are electron releasing by resonance, which means I have basically sabotaged this dienophile. I've basically sabotaged this dienophile because I've stuck on it 2 strongly electron releasing groups. Dienophiles are activated by electron withdrawing groups, which means putting on electron releasing groups does the other thing, which is to make them less active. So this is going to be a very, very difficult reaction. In other words, I'm going to have to use 300 degrees Celsius for 5 days to get any kind of yield of this product. On the other hand, if I go the method on the right, on the left, my diene is activated. It's significantly activated because I have 2 strongly electron releasing groups on it. My dienophile is not activated, but at least my dienophile is. My diene is. So in this reaction, it is favored, so my timer is beeping, so it's time for us to stop. But the preferred pathway is actually the pathway on the left, where I have an activated diene and an ordinary dienophile giving rise to this species. I'll do a selective reduction and make my product. That is much preferred over using a strongly deactivated dienophile and an unactivated diene. Okay? So there are certain strategies involved in doing these order reactions. So at this point we're going to stop, and we will pick up at this point on Wednesday, and we will spend another 15-20 minutes, I think, and complete the discussion on these order. I'm going to ask you guys a favor, which is I would like you guys to sort of critique how this exercise went. In other words, did you think the presentation was fine? Could you follow what I was doing? And would you recommend that I do this in the future? Because what I'm actually thinking of doing is taping my organic lectures using this forum. I would run the lectures in class and simply use the laptop, the tablet, to write stuff on, and then post my lectures on Blackboard so that students can see it both in the actual classroom, and then later on, if they want to, instead of listening to the tape recorder, they could simply go back and view it on Blackboard. But let me know how this works, and I'd appreciate your feedback. So thank you guys very much. Enjoy your weekend, and I'll see you guys on Monday. Be good. Don't do anything I wouldn't do, which is a lot. And I'll see you guys later. God bless.